This is section 2.7, limits at infinity and horizontal asymptotes. We will learn how to explicitly calculate the limits at infinity of a function and also how to find a horizontal asymptotes of a certain function. First of all, let's look at the previous situation, the infinite limits. We remember if, for instance, the number is not in the domain of the function, and we do have this rational function, 3 minus x over 1 minus x, and we can see that x equals to 1. This is not in the domain, and we would like to investigate the behavior near 1. And we know that if x is approaching 1 from the left-hand side, we will have 3 minus 1, 2, 1 minus 1, 0. However, 1 from the left-hand side is like 0.9. We will get 1 minus 0.9. We will actually get positive value, small number, but positive 0. Of course, this is just the limit, it's not actual 0. And 2 over small number is a big number. And that's the infinite limit. We know that we will have a vertical asymptote on the left-hand side. Let's also check the right-hand side. On the right-hand side, we have 3 minus 1 is 2, 1 minus 1 is 0. However, that 1 is 1.1, 1.01, and so on. The value will be negative, tiny, but negative. 2 over small number is a big number, but negative. Okay, that means that's the infinite limits. And we will not draw the entire function because we don't have enough information, but at 1, we do have a clear situation. As x is approaching 1, as the values are approaching 1, from the left-hand side, the value of the function will actually go up, positive infinity. As x is getting closer and closer to 1 from the right-hand side, values of the function will go down. But we do have a little bit of situation. Okay? And definitely x equals to 1 is a vertical asymptote. Okay, now let's look at the situation of the, like, what is happening with the function as x is getting actually big, large, arbitrarily large, and using mathematical symbols as x is approaching infinity, because infinity represents huge number, of course, positive or negative. Yeah? We will investigate how function behaves. And we may notice this is like end of the number line. This is the other end of the number line. That's the reason that we call this end behavior. Like, other values like increasing without the bounds, or maybe we do have a certain like limitations, certain like bounds, limits, then we will create the asymptotic situation in the horizontal way. Okay, let's look at this. Oh, okay. Oh, too fast. Okay. One of the easiest rational function is 1 over x, hyperbola in the first and the third quadrant. We can see the graph in the corner. And looking at the graph, we can see right away a vertical asymptote. We know this. It's 0 because as x is approaching, first of all, 0 is not in the domain. As x is approaching 0 from the left and from the right, we will have 1 over 0, small number negatives, 1 over small is big, but negative. And we may notice function is going down on the left-hand side. On the right-hand side, 1 over small number is the big numbers, infinity. We have infinite limits. This results in the vertical asymptotes. Now, let's check how the blue curve, the function, behaves as x is getting arbitrarily large, as x is approaching infinity. X approaches infinity. And we may notice the values, the graph of the function is getting lower and lower and lower, and it's approaching basically the x-axis, and the x-axis is the 0. That's the value 0. We'll never touch the x-axis, but it's approaching, because when we will think numerically, 1/1 is 1, 1/2, 1/2, 1/3, 1/4, 1/5, 1/6, 1/10, 1/1,000,000, 1/1,000,000,000. We're getting small numbers. 1/big number, and I can write this really informally, 1/big number, it will be small. And that is that 0, that green line is that 0. Function will never touch it, but that's the limit. And again, 1/big number. This one was positive, this one is negative, but we can see also from the negative side, from below the x-axis, but also the graph is approaching 0 as x is getting large in the negative direction. -1/2, -1/4, -1/8, -1/100, small numbers. Numerically, when we divide 1/big number, we will get small. Okay, and that's the limits at infinity we did investigate. And of course, the resulting line is a line y equals to 0, because this is the y values. That's the y values. Y equals to 0. And this is horizontal asymptote. Horizontal asymptote. If we will be asked to find the horizontal asymptote, we have to investigate limits at infinity. We have to compute the limit at infinity of the function. And now we will try to find out the nice explicit way of computing these limits. First of all, let's define properly. Let f be a function defined on some interval from a to infinity. This means we do have infinity as an end of the domain. Then we may say that the limit as x is approaching infinity of the function f of x is equal to L. And this means that function can be made arbitrarily close to L by taking x sufficiently large. And we have, of course, we're using infinity as a symbol. Infinity is not representing any number. We will not play with infinity in arithmetic. Especially infinity minus infinity can give us some problems, but we will investigate this also. And we can, yes, we may choose any description we like. Limit of f of x as x approaches infinity is L, for instance. Or we may have the other side. We may have a function defined from negative infinity to a, and then we will say that the limit as x approaches negative infinity of the function f of x equals to L. This means that values f of x can be made arbitrarily close to L by taking x sufficiently large in the negative direction. Okay, and now we may have the same limit, or we may actually have also different limits at both, but actually I can maybe adjust a little bit. We may have a line, let's say the line y equals to L is called horizontal asymptote if the limit at infinity of the function is equal to that L. But we may have also both of the L's could be different at positive infinity and at negative infinity. We may have different values, and we will have different horizontal asymptotes. And the maximum number of horizontal asymptotes are 2, because we have 2 endpoints, 2 different. We may have the same horizontal asymptote, or we may have a different. And yes, that's the one thing that is important. Possibly I do have. Actually, let me draw different and let me draw the same. We may have, let's say this is our L line. Yeah, that's L, y, x. And now function let's draw a function, because this indicates that the behavior of the function only at infinities, positive and negative, is L. And that's how we can respect this definition. Okay, that means I can see functions approaching, and then let's say this. That's we may notice I did intersect the asymptote y equals to L, and this is perfectly fine. But at infinities, it's definitely the limit L. Function will go arbitrarily close as x is getting bigger and bigger. And that's one thing. And as I mentioned, we may have different limit. Let's say this will stay L, or maybe this could be negative L. Yeah, that sometimes happens. We will have opposite. And then our graph, yeah, let's respect the asymptote at infinities. I can have this maybe example. Oh, this is a nice function. So we can see again, I'm respecting at infinities, the function is approaching the dotted line. It will never touch it. But I also have some intersection. That's one thing that we may be confused, but not from now. From now, all is nice and clear. Okay, couple of examples. Now we can see different asymptotes. We intersecting here. We may even intersect, like we may intersect a couple of times. So we may see, for instance, let's say 1, 2, 3, 4, 5, and 6. For instance, 5, the function 5, definitely have a limit at infinity, on a negative infinity only, because at positive infinity function goes down, doesn't have a horizontal asymptote. Function 6 has the 2 and negative 1 horizontal asymptotes at negative infinity and positive infinity respectively. And of course, really interesting function is function number 3. We will also call that line, horizontal line L, is an asymptote, even if we have multiple like intersection, but eventually the function is approaching. We can see it's kind of like a snake getting smaller and smaller, and it's approaching a line. Okay, now let's look at this numerical approach. If we will take a rational function 1 over x to the power of r is a positive number. It could be any number. I can just say positive, like positive integers, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's x to the power of a positive number. Then we not flipping a fraction. We don't have any other form. It will be just 1 over a number, 1 over big number. Yeah? I mean, again, 1 over x to the power of a positive number. If we would like to compute the behavior at infinity at the big numbers, we of course, we getting 1 over big, we will always get 0. This will disappear. This eventually at infinity, we will get this probably it's a negative because it will be, depends of course, depends on, could be positive, could be negative, depends on the power r, because if the power r is even, we will have maybe positive big number. However, 1 over big again is small because we don't have positive, negative, 0. I mean, it's worth to remember that this type of function completely like disappeared, becomes like 0. I mean, not disappeared, is the values. The values are getting smaller and smaller and smaller. It will never become 0, but extremely small number, sufficiently close to 0 as x is getting arbitrarily large, sufficiently large. Hey, 1 over big is small. Now let's try to compute the limits. Limit as x approaches infinity, 1 over x minus 5. We can see x is a big number, infinity, And subtracting 5 or adding 5, subtracting 50 or adding 50 or any other constant will not really change the number. We will still have the situation 1 over big is small. This limit is basically 0. Okay? Of course, what we will do now for the next couple of minutes, we will try to compute limits at infinity explicitly. We still have to understand the concept, the behavior of the function, the asymptotic behavior, but let's master computation. Okay, but what I will do, I can show you, we know, you can tell me right away this answer is 0 because it's 1 over big. If we understand this, it's perfectly fine. But I will prove it using the algebra. I mean, I will take that x because this is the leading function, leading term in the denominator, and I will factor out. Yeah, we can see factoring out x, we're getting 1 because 1 times x is x, and 1 times 5 over x, it's still 5. I mean, we're good with this part of algebra. And now we may notice 5, yes, we're getting 5 over x, 5 over big number, of course, is 0. And then 1 over 1, and then we're getting 1 over x. And this, we have no problem. 1 over x is 0. 1 over small number is 0. Then we can put this. Yeah. But again, if you know the answer right away, you don't have to even have this algebraic proof. Okay, let's look at the next one. Limit as x goes to the infinity, 2x minus 1 over 4x squared plus 5. This one looks a little bit complicated because 2x minus 1 is the linear function, and this function goes to the infinity. I can maybe write here. And quadratic function, 2x squared plus 5, as x is getting big, the values are also getting big. We have the situation infinity over infinity. We do remember from section 2.5 indeterminate forms. This is one of the indeterminate forms. We have to make it like more clear. What we can do, I can use exactly the same tool that I use it in example 1. I will look at the leading function, which is 2x on the top, 4x squared in the denominator. And I will factor out just the function, not the coefficient. I will factor x on the top and x squared in the denominator. Yeah, just factor out. Again, 2, x times 2 is 2x, x times 1 over x is 1. X squared times 4, 4x squared, x squared plus 5 over x squared is just 5. Okay, as we know, we are okay with this factorization. Okay, and now let's investigate what we have. We have 1 over x, 1 over big, small. 5 over big, also small. Doesn't matter if it's 5 or 6, the big number will take a lead. Again, all of these terms kind of like disappeared. 2 and 4, that's the constant. But what is important, we end up having x over x squared. Now we can cancel out, because now we have a product, we can cancel out. X over x squared is 1 over x, 1 over big. Again, 1 over big is small, we have the answer 0. Yes, we have the answer 0, the same like this one, 1 over x, 1 over big. Okay, let's do one more and we will make a couple of conclusions. Okay, we have 5x cubed plus x squared minus 1, x to the power of 4 minus x cubed plus 2 in the denominator, and x is big. We may notice the same thing, polynomials, cube function goes to the infinity up, and the 4th degree polynomial also goes to the infinity, infinity over infinity. And we don't know what it is, we have to investigate. And let's do the same thing. Let's focus on the leading terms, the highest power, x cubed and x to the power of 4. Let's factor out. Factoring out x cubed, we will have 5, x squared over x cubed, 1 over x cubed. And then 1, x cubed over x to the power of 4, 2 over x to the power of 4. And again, we may notice the zeros, 0, 0, 0, 0, because we will get 1 over big number or 2 over big number. That's zeros. What's left? Leading coefficients, 5 and 1, it's okay, but product at the front is important, x cubed over x to the power of 4. After cancellation, we will get 1 over x, 1 over big number is a small number, okay? That means, first of all, we don't have to do this all the time, but we may notice that having a ratio of 2 polynomials, which is and x is approaching infinity, of course, big numbers, we will get the ratio of the function infinity over infinity, indeterminate form. Looking at these algebraic steps, we may notice that only the leading function are important, because the rest of the terms, the lower degree expressions, completely disappeared. Like we will see 0, we will get 0, but only the leading terms are important, leading function. So we always have to look at the leading function and investigate the limited infinity based on the leading function, okay? And one of the conclusions also is, if the denominator has a stronger power, if the denominators are winning, we will always get 0. If the denominators are winning with respect to the degree of the polynomial, always 0, because we will algebraically cancel out, and always denominator will be bigger, big 1 over big, small 0. Okay? If the degree is less in the numerator, the limited infinity is always 0. And for instance, I have number 4. You may try to answer before me. You can pause the video now and you can try to answer. We can see 3x to the power of 5, leading function, x to the power of 7, x to the power of 5, x to the power of 7. Of course, denominator is winning, the limit will be 0. And x is approaching infinity. And just maybe adding the concept of horizontal asymptotes, all of these zeros represents the horizontal asymptote. Horizontal asymptote at positive infinity, because we just investigated positive infinity. Okay, horizontal asymptote. Function will, y equals to 0. Okay. Let's look at this slide. X is approaching infinity, and we have 3x plus 5 over x minus 4. Looking at the degree of the polynomials, none of them is winning. Is x to the power of 1 on the top and x to the power of 1 in the denominator. They are the same. So let's see what's happened if we will factor out that leading functions respectively on the numerator and denominator. Factoring out x, we're getting 3 plus 5 over x and 1 minus 4 over x. The same thing, this will become 0, this will become 0. And since they are the same function, we may cancel them out. Yeah, it will be just 1 and 1. And what stays? The leading coefficient, 3 and 1. So we can see the answer will be 3 over 1, 3. Let's look at the second one. Limit as x goes to the infinity, 2 minus 3x squared over 5x squared plus 4x. Okay. Leading, the same, we can see the same thing. Leading function is negative 3x squared. Leading function in the denominator, 5x squared. X squared, the same. Let's factor out x squared. 2 over x squared minus 3, 5 plus 4x over x squared. Everything what has denominator bigger, 0, 0. Of course, this situation is at infinities only. And the same leading function, maybe I can use red, can be cancelled out. And what is important? Important is the leading coefficients, ratio of the leading coefficients, negative 3 over 5. Yeah. Another conclusion. For the rational function with the same degree, polynomials on the top and the bottom, the ratio of the leading coefficients will give us the answer for the limits at infinity. Okay, if the degree of the polynomial in the numerator and denominator is the same, the limit at infinity, that limit at infinity, of course, is just the ratio of the leading coefficients, the coefficient from the leading functions. And for instance, again, you may pause the video and try to answer, try to compute the limit number 7 before I did. Okay, are you pausing the video? I hope. And then you can come back. Okay, you come back. And first of all, we can see 4x to the power of 4. I can limits at infinity, 4x to the power of 4. And theoretically, we're not interested in the other terms because only leading terms, leading functions are taking lead in these examples. When I distribute everything in the denominator, we will have 4x to the power of 4, and we may see, and the rest of the terms we're not interested because they will become 0, only the leading terms. And actually they are the same, the limit is 1. I hope you also got 1. Okay, and I have couple of those examples. Let's look at them. Yeah, you will be an expert with computing limits at infinity. Ratio of x plus 2 over square root of 9x squared plus 1. Limits at infinity. The same. Linear function, root function, they go to infinity. We have infinity over infinity. Now, I'm not sure if it's easy to distinguish the degree because x to the power of 1 on the top, but in the denominator, we have square root of 9x squared. We may apply the square root to the 9x squared, and that's actually will be our leading term. But let's look at this algebraically. Okay, I factor out x because that's the leading function, and then 1 plus 2 over x. And I also factor out square root of x squared because product, we can keep it like under the square root. That's mean 9 plus 1 over x squared. And of course, this goes to 0, this goes to 0. And what stays? Square root of x squared. We know that x goes to the positive infinity, then we have no problem. We can cancel out this x. Oh, too fast. We can cancel out x and squared. And now the leading functions are actually the same degree, x and x. We can cancel them out. That means square root of the x squared at positive infinity will give us x, the same degree. And the leading coefficients, of course, are important. Square root of 9 is 3, 1 over 3. Okay. Let's look at this one. The same thing. Algebraically, we can factor out everything, but we may see this is the leading function that I didn't type. I can maybe limits at infinity and then 8x, and we're not interesting. And after factoring out everything, this will be the leading term, square root of 4x squared. And the rest of them, it will be 1, and then we're not interested. I can still have, this is 8x plus the rest of the stuff, and this will be square root of 4, 2, and square root, again, of x squared. This is x, but only as x is positive infinity. I can say 2x, and the rest of the stuff. Okay, 1/4. Now, let's look at the same function, square root of 4x squared minus 1 over 8x minus 3. However, we would like to check the behavior at negative infinity because this function is also defined at negative infinity. Okay, we will do the same thing. Yeah, we will have, let's look at the leading coefficient, leading function, 8x, and we're not interesting. Square root of 4, square root of x squared. I just did this way. And now what we will have, let me copy one more time. We will have 8x, 2, And now square root of the x squared. If x is negative infinity, it will be negative because that x itself, that x is negative. With extra negative, we will make positive. This, again, still, I mean, we didn't change anything with respect to the sign. The sign of the numerator is positive. Even if it looks like this blue negative x, now it's still positive because x itself is negative, because x is approaching negative infinity. Okay, negative 1/4 will be the answer after cancelling 2/8 and x over negative x. Okay, so now please look at this. It's really important when we have to simplify the absolute value, the square root. If we know that quantity x is positive, we can simplify like no problem. But if we know that quantity x is negative, then we will put negative x to make it positive. Or in general, we can put absolute value and then go from there. We were solving a couple of limits with absolute value. Okay. And then I have a list of couple of questions. You may try to solve them. Okay? I can add the solution later. Okay? Or we may pick one, like for instance, let's say this one. All of them are limits at infinity, positive or negative. That's when we know what is the algorithm. Leading function. Well, let's do cube root of 8, cube root of x to the power of 6, 4x squared, because we only interested at leading terms. 2, cube root of x to the power of 6 will give us x squared, and 4x squared, I suppose, to have a limit. And limit at infinity, positive infinity. Okay, the limit is 1/2 because it's the same degree ratio of the leading coefficient. And that's how you can do with all of them. Okay? Which one is negative? Negative infinity, we have to be careful because this will be 2x, no problem, we're not changing anything. Negative infinity, let x goes to negative infinity. Square root of 16 is 4, and square root of x squared. This will give us, I will copy one more time, 2x, 4, and negative x, because that's the simplification, okay? X and x is gone, negative 2 is the final answer. And of course, all of these answers are the horizontal asymptotes. Okay, you may play with this. Please remember, okay? Please remember to apply the negative. And just all of them, I believe, all of them has the same degree. We have to figure out the ratio of the leading coefficients and the correct simplification of the square root expression. Okay, and then I have a couple of these limits. Okay. How function sine of x behaves at infinity. We all know function sine, nice sine curve, oh, a little bit not symmetric, 0, 1, and negative 1. And we may notice function sine is like oscillating between the value like 1, negative 1, 1, negative 1, 1, negative 1. Yeah? We may say that limit at infinity does not approach a finite number. And function sine of x doesn't have an asymptote, horizontal asymptote, because the limit at infinity is undefined. Okay, now we have sine of 1 over x. Function sine is a continuous function that we know that we may just compute a limit of the inner function of this. Yeah, we can check how this expression behaves at infinity and then apply to the sine. And of course, 1 over big number is a small number. Sine of 0 is 0. Okay. And actually number 19, I think it is in our, but let's wait, I'm just looking now, let's wait until section 4.5, because this is infinity, right? X goes to infinity times sine of 1 over x, we just did it. This limit is 0. Infinity times 0 is another indeterminate form, okay? That we will hold with this one for a second. Also, we may try to compute the limits at infinity of a certain function and actually get infinity. We will call infinite limits at infinity. And one of the basic functions are the polynomials. Let's say x cubed. Yeah, function x cubed, we know how function, too low. Function x cubed goes to, as x is big, the values are getting big. We may also think arithmetically, infinity, like huge numbers cube. Yeah? It's of course huge number. I mean, this goes to the infinity. As x is getting large in the negative direction, when we will cube negative numbers, we will get negative numbers. Go down, and this one go up. Yeah? We will call infinite limits at infinity, of course, no horizontal asymptote. And okay, I have a couple of limits. X cubed at infinity goes to the infinity. X cubed at negative infinity goes to the negative infinity. Okay, 22, we do have a small problem because parabola x squared goes to the infinity and line goes to the infinity. We have infinity minus infinity. Indeterminate form, but let's try to take care of this one. We will not wait for the section 4.5 because section 4.5 talks deeper about all indeterminate forms. Since we're doing this, okay, because we do have tools for this one. Of course, infinity minus infinity, is indeterminate form. The answer could be anything, could be 0, could be 1, could be any non-zero finite number, could be infinity, or could be negative infinity. But we have to rewrite, we cannot leave it like this. And what I will do, since we just learned that we may play with the leading functions, I will factor out x over x squared. Of course, it's 1 over x. And let's see what's happened. This will go to 0 because simplifying, we will get 1 over x, 1 over big is small number. And we will just end up with x squared times 1, x squared. And x squared is not indeterminate form. At infinity, it goes to the infinity. Okay, that's one way, yeah, to rewrite and to prove it, that we do have a certain answer, but please do not guess this answer negative. I mean infinity minus infinity. Okay, similar situation. This is infinity and this is infinity. Okay, we may try to play with the leading coefficients, but what we also learn, I'm just trying to think. We may, because, okay, to the point. We learn having limits with the square root expression. We know that we may use the conjugate expression to rewrite them. And that's what I will do. I will copy this square root of x squared plus x minus x like this, and I will multiply and divide by the conjugate expression. Square root of x squared plus x and square root of x squared plus x, because that's the sign that we change it. Okay, and because I'm not changing the original settings, original expression, not at all. But let's see what's happened. Then I have x squared plus x plus x. Okay, easier. When I factor out everything, when I FOIL the numerator, we will square the first quantity, x squared plus x, under the square root, squared, the square root is gone, and minus x squared, because we will square the second quantity. Now let's try to look what we have. We may notice x squared minus x squared, okay. And now we have x, and when we factor out the leading coefficient from this, it's square root of x squared. That's because we know that we have to just look at the leading. And we can simplify. Well, that means after simplifying, we will just get x, because square root of x squared is x if x is positive, and x is positive. And also we do have another x plus, because that's expanded form, plus x. I mean, this came from the leading coefficient, leading function. And we have the same function, x over 2x, it will be 1/2, right? Because we can simplify, this will be 2x, x's can be cancelled out, and 1/2. So we can see it's interesting, infinity minus infinity, that's how we started, and we have finite number. Yeah? This function will have a horizontal asymptote 1/2 at infinity, probably negative 1/2 at negative infinity. You may try to compute this. Or maybe this function is not defined at negative infinity. Yeah, because we, oh no, maybe it is. You may try to find out what is the limit at negative infinity. I'm just looking, but okay, just to clarify, this infinity minus infinity was indeterminate form, and doing some steps, we did get a finite number. Okay, now limit 24 and 25. Let's finish the session with this, and we will have also additional session focusing on a little bit deeper on horizontal asymptotes only, because now you are the expert with computing the limits at infinity. Okay, how function e to the x behaves at infinity? Of course, it's infinity. How logarithmic function behaves as x is getting large is also infinity. I can maybe draw a teeny tiny graphs, e to the x. We know how this function grows extremely fast. Yes, that's the exponential function. And logarithmic function is also increasing, but really slow, because it's the opposite function, inverse function to inverse to e to the x. So in both of them are approaching infinity, logarithmic really slow, exponential really fast. Okay, thank you very much, and please check the second video about the horizontal asymptotes. Thank you.